Good day. We are AJ, FL, Mark, and Justin, and we will be presenting our take on self-regulating water heater. Inspired by the thesis of Kusho et al., we aim to create a cross-project with ENG 181.31 and ENG 183.3X to develop a closed-loop automated system that utilizes lessons from all three subjects, creating a heat mechanism that will always aim to match the set point. Specifically, we hope to use electronic devices and our circuit making abilities from this class to cascade and connect microprocessors, sensors, and a heating coil to make this system possible. As an overview of the system, we hope to use a 240-volt, 60 Hz AC main to power the actuator with the FPGA sending a trigger signal to the solid-state relay in order to control the duty cycles, which will adjust the average voltage that passes through the water heater or heating coil that will heat the water. A DS18B20 temperature sensor will communicate to the FPGA a feedback signal that allows the device to gather this data. This is where the SPI communication will come in with the FPGA as a slave and the ESP the master. The FPGA will simultaneously send over this information to the ESP while it also calculates a control signal using PID functions that would ultimately determine the timing of the SSR. Moving into the ESP, it connects to a database in Cloud Firebase where it takes values of the temperature detected via SPI and the MCP 9808 where real-time data of measured temperature and the desired temperature is sent to the LCD. I2C communication buses are used to communicate the ESP between the connected devices seen on the right-hand side. The system overview showcases the setup from the ESP to the FPGA all the way to the water heater via coil.
Let's talk about the hardware used for this project. First, we had to use a FPGA as the controller, and the Tang Nano 9K was chosen due to its small size and simplicity. It costs 929 pesos. Now, for the actuator, we bought a portable water heater that uses AC mains as input. It costs 72 pesos. Then, we thought of using a solid state relay which uses a triac and an optocoupler so that the AC loads can be switched by 3.3 DC logic from the FPGA. Of course, we had to place the relay on a proper enclosure with other materials. All in all, it costs 298 pesos. Now, for the temperature sensor that we used is a DS18B20, which is cheap and also waterproof. It costs 59 pesos. We also bought two ESP32s, an LCD module, and an air temperature sensor, which costs 1,197 pesos in total. Lastly, we had to buy breadboards, jumper wires, and a charger to connect and to power the hardware. It costs 406 pesos. All in all, we spent around 2,961 pesos for this project. For the FPGA side of the project, we had four goals. First, to get the water temperature data. Second, to send this data to the ESP32. Third, to get user-defined values from ESP32. Then lastly, to control the actuator based on the current water temperature and the set point. To obtain the water temperature data, we knew that the chosen sensor can send digital data due to its transducer. However, its communication is complex as it is timing based. Hence, we designed a finite state machine in the FPGA to get this data.
The SPI or the serial peripheral interface is a way to synchronously and serially communicate between two devices. And the two devices that we used are the ESP32 and the FPGA. In our implementation, we made the ESP32 the master, which controls the clock and the chip select, and the FPGA is the slave. The PID or the proportional integral derivative controller is a way to generate the proper response to correct the current error that is in the system. And the way we program the output is by means of time proportional control, in which it works very similarly to PWM. So as the value of the response goes higher, the duty cycle also goes higher.
Next, I will discuss the ESP32 network consisting of the dashboard ESP32 located at the bottom right of the breadboard and the SPI ESP32 located at the top of the breadboard. The dashboard ESP32 provides the user interface through a web dashboard, while the SPI ESP32 sends the PID gain coefficients and set point to the FPGA. The two ESP32s communicate with each other over the internet through the Firebase real-time database. The database stores the values of the PID and setpoint settings, as well as the feedback, water, and ambient temperatures. This slide shows the interface of the web dashboard. It displays the current water and ambient temperatures and accepts changes to the setpoint and PID gain coefficients. When a user enters an unacceptable value for any of the input fields, The web server generates an error message and does not transfer the erroneous information to the FPGA. On the other hand, this slide shows the Firebase real-time database, which stores the current readings and settings. Our chosen cloud provider hosts our database in Singapore, which is the nearest available server from the Philippines to ensure the lowest latency. Although not recommended, changes to the PID gain coefficients and setpoint can be done here as well.
This demo shows that the feedback system works well, exhibiting small deviations from the set point bouncing around between 49.8 degrees and 50.1 degrees. This demo shows that the feedback system works well, exhibiting small deviations from the set point bouncing around between 49.8 degrees and 50.1 degrees. This demo demonstrates that varying the gain values of PID will also vary the temperature sent to the coil as seen from the LCD and web dashboard. This demo demonstrates that varying the gain values of PID will also vary the temperature sent to the coil. This demo shows that the water heating works well with our system.
Conclude, the FPGA can be used as an alternative to microcontrollers and PLCs to start from scratch. An example of this is the SPI controller, in which we could implement one that has different characteristics from those that are already in the market. We can also control AC loads like that of the water heater, in which 3.3 volts could be used to control it with the help of a solid state relay. And as seen a while ago in the demo, it could be seen that the system is working properly and the response approached steady state. For the social impact, our main inspiration is Kusho et al.'s research, which is incubating E. coli for water quality testing. And in terms of energy efficiency, by implementing PIDs, we could appropriately make use of energy by turning off the heater when approaching the correct temperature. And for healthcare, there are also medical equipments and applications in which proper, precise, and accurate control over temperature is needed. I was the one who created the PID and the SPI modules in Verilog, and the main inspiration of the PID was the PID library of the Arduino, and the SPI was made from scratch based on simply knowing how it works. And I was also the one who tested the two modules through the use of the test bench through the simulation of Model Sim. And I'm really glad that this worked out, even though we had to spend a lot of time trying to debug and conceptualize how all things would work.